detail. So we will get idea how the mechanism is formed. Okay, so let's start with
Just
the
sorry,
types
sir.
of constraint motion. There are three types of constraint motion. One is completely constraint motion. Completely constraint motion is that whenever motion between two elements of a pair is in definite direction irrespective of force applied. So let's try to understand this definition through these two examples. So I have one shaft, square shaft, and a square hole, and this square shaft can just translate in this square hole. It cannot rotate in the square hole, right? So irrespective of direction of force applied, whether you apply force from this direction or from this direction, this square shaft will just translate in this square hole, right? So irrespective of direction of force applied, the motion between these two elements is in the definite direction. Similarly, take an example. We have circular shaft in a circular hole. The shaft is with collars. So as collars are there, so these are the collars to the shaft. They are avoiding the translatory motion of the shaft. So this shaft cannot translate in this hole. It can just rotate. So we are completely constraining the motion in the rotating direction, right? And that's why we can say that it is completely constrained motion. So this is the first type of constrained motion. Second type of constrained motion is incompletely constrained motion. Incompletely constrained motion is that when the motion between the two elements of a pair is possible in more than one direction, depending on what kind of force we are applying. So this is an example of square shaft, the circular shaft and circular hole. So here, if I rotate this shaft,
you are currently the only person
here
in
if
this
I
conference.
rotate this shaft, obviously we'll get a rotatory motion in between shaft and hole. But if I apply the longitudinal force to it, then basically this shaft will translate in this hole. So we can have both rotating as well as translatory motion possible depending on what kind of force we are applying. Okay, so this is the second type of motion. The third type of motion is successfully constrained motion. In this case, the motion between two elements of a pair is possible in more than one direction, but made to have motion in one direction only because of some external or mechanical conditions, you can say. So for example, let's take an example of the IC engine, which we have studied in the previous slide. We have in IC engine, we have a piston cylinder arrangement, right? We have a piston cylinder arrangement. The piston is able to rotate as well as translate, but in IC engine, it will not rotate, it will just translate within the cylinder, right? So we are successfully constraining the motion in one direction. So motion between the two elements of pair is possible here in both direction, but we are making sure that it is performing motion only in one direction. And also on the other side, I have one more example of a the bearing, footstep bearing, where we can see depending on load applied in the footstep bearing, we have only vertical motion, though it is possible to have rotatory motion as well. But in footstep bearing, we can say vertical motion is there only, not the rotatory motion. Hence, we can say that in this case also we are successfully constraining the motion because of some external constraints. So these are the different types of constraint motions. So we understood the motion. Now it's time to understand the concept of rigid body. The concept of rigid body, because in order to make a mechanism, we need rigid bodies. We have to combine the rigid bodies together or assemble them. A rigid and resistance body. So what is rigid body and what is resistant body? The name itself indicate meaning that rigid body is that under the action of forces, it will not suffer any distortion. Okay, or the body suppose is like this. If you are applying the force, even after applying the force, it is not getting distorted. Means you can see if you take any 2 points within these two body, the distance between these 2 points will remain same even after application of the force. Then we'll say it as a rigid body. Okay, but in reality, the rigid bodies are very rare. So in real situation we use resistant bodies. So what are resistant bodies? Resistant bodies are those which are rigid for the purpose they have to serve. Okay, they are not always rigid, but they are rigid for the purpose they have to serve. So let's take an example. What is the purpose of belt? And yeah, we use belt in order to connect the pulleys, and they are under tensile action. So whenever belts are under the tensile action, they act as a rigid body. So I will say that belt is rigid when subjected to the tensile forces. Similarly, fluid can also act as a rigid body when it is subjected to the compressive load. Okay, we know the hydraulic press we use in order to lift the machines from one side if you apply the force on the other side. So basically in hydraulic press we use the compressive loading on the fluid, and at that time fluid will act as a rigid body. Okay, so this is the difference between resistant bodies and rigid body. Yeah, but yeah, in general resistant bodies are rigid bodies only because we are using them for the purpose. So we can consider them as rigid bodies as well for the purpose we have to serve. So now let's try to understand the link, the concept of link. Mechanism is made up of the number of resistant bodies. Okay, and then how the link is related to this rigid body is like we can say combination of member of mechanism. Okay, so for example, a piston cylinder arrangement or a single slider crank chain mechanism. Okay, so this is a single slider crank mechanism. Link 1 is fixed, link 2 is suppose crank, link 3 is connecting rod, and link 4 is piston. So these are all links. So we can say link is nothing but a resistant body or a group of resistant body. It can be a group of resistant bodies. So here the example which I have given is a binary link, because for example, if I take a crank here, the crank is having two ends. If I take a connecting rod, that is also having two ends. Okay, but a link can be binary link like this. It can be a tertiary link like this. Okay, or it can be a quaternary link, depending on how many other links it can connect. We can have different types of link: binary, quaternary, tertiary, and so on. Okay, so basically a link can be a single rigid body or it can be a consist of more than one rigid bodies as well. So whenever we say a link, it means we are talking about the rigid body only. So we got the concept of rigid body and link. Now it's time to understand the concept of pair, how we can pair these links together, how we can combine or connect these links together. Because in order to make a mechanism, we have to connect these links together and assemble them. So we should understand how we can connect them. Okay, so this is what I have explained just now, types of links. So we were discussing about the kinematic pair. Kinematic pair is the joint between two links, and different types of kinematic pairs are there depending on the type of contact between them, type of mechanical constraint, and nature of relative motion. So kinematic pair is nothing but a joint of two links, and their types are nature of contact. Depending on nature of contact, we have different kind of links. Nature of mechanical constraint, depending on the relative motion between the links. We have different type of the kinematic pair. So first, depending on type of contact, either we can have lower pair or higher pair. What is lower and higher pair? Whenever we have the surface contact between the two members or two links, we can say it as lower pair. Okay, and whenever we have point or line contact, then we say it as a higher pair. So let's take an example of a ball bearing or roller bearing. Whenever a ball bearing is or roller bearing is moving inside the rest, it is having a either point contact. So ball bearing will have point contact, and roller bearing will have, we can say, makes a higher pair. Whereas if you take an example of slider crank chain, okay, or nut turning in the screw, okay, and shaft is, for example, rotating in a bearing, all these are examples of a lower pair where we can say these the two members are having a surface contact between them. Okay, so that is the differentiation between lower and higher pair. Coming towards the second type, that is depending on the nature of mechanical constraint, we have closed or unclosed pair. Let me go to the next slide to explain this. Depending on the nature of mechanical constraint, and this is unclosed. So from figures we can clearly see in the second figure, cam and follower are not closed, right? We can easily separate these two links. Okay, we can easily separate these two links. So now, if you take the first link, if you take the first link of the closed pair, here we can see so we have to break follower in order to separate them. We cannot, let's say, easily separate cam and follower. So the elements of pair like cam and follower are held together mechanically, and that's why we have to call it as a closed pair. Okay, and but whenever the elements of pair are not held together mechanically, they are just together because of the gravity or spring action, then we can say them as a unclosed pair. And Coming towards the third classification of the kinematic pair is depending on the relative motion, sliding pair. Okay, different types where we can have sliding motion between them, between the two links. Here the example of rectangular shaft sliding in a rectangular hole. We can have a turning pair. Okay, where we can see the circular shaft is turning that shaft is with collar, so it can just rotate. So whenever one link is having turning on or revolving motion related to other, we call it as a turning pair. The third is, you can say, rolling pair. Good example is ball bearing is rolling inside the recess. The next one is the screw pair. Screw pair is whenever two links they have both turning as well as sliding motion between them, we call them as a screw pair. And the last one is the spherical pair, where one link is in the form of sphere and pair. So these are the 5 different kinds of possible pairs depending on the nature of relative motion. So this is broad classification of the um, kinematic pairs. So now we understood some terminologies, we understood the link, we understood how to make the joint. So basically a kinematic pair. And let's try to understand the joints. So either we can have a binary joint, okay? We can have either a binary joint, or we can have a tertiary joint, or we can have a quaternary joint. Okay. Whenever 3 links are joined together, we call it as tertiary joint. Or ternary joint, we can say. Ternary joint. And whenever 4 links are joined together, we call it as a quaternary joint. Okay. One tertiary joint or one ternary joint is equivalent to 2 binary joints, and one quaternary joint is equivalent to 3 binary joints. Okay, so this is the relationship we should know. And why is because whenever we are supposed to calculate the degrees of freedom, we should understand what is the equivalence between the binary and tertiary and quaternary joints. So now we understood the links and pairs, and we made
You are currently the only person in this conference.
Yeah. So making the joints is not only the purpose. Here we should have a constraint motion between the links. That is also equally important. So we should understand the concept of degrees of freedom. Degrees of freedom. Degree of freedom of a pair, we can say, is a number of independent relative motion a pair can have. Okay, it can be either translatory motion or rotatory motion. Okay, so if you take any rigid body and in a space, it will have 6 degrees of freedom. It will translate in x direction, translate in y direction, and it will also translate in z direction. Okay, so these 3 translatory degrees of freedom and 3 rotating degrees of freedom, because the body can rotate in about x-axis, about y-axis, and about z-axis. So total 6 degrees of freedom we have, and degrees of freedom of a pair can be calculated as 6 minus number of restraints, okay, or constraints we can say. So for example, if I am constraining the motion of a body only in one direction, okay, so for example, this is shaft and this is hole. So here this shaft can have a translatory motion about x-axis. Okay, in the x-axis, this x-axis for example, so it will translate either in x-axis or it will rotate about x-axis. But we are making sure that it will not translate in y direction, z direction, rotate about y direction, z direction. So basically we are putting 4 constraints on it. So 6 minus 4 are 2. There are total 2 degrees of freedom in this, and that is translation in x direction and the rotation about x direction. If I put a collars on it, okay, if I put a collars on this shaft, then what will happen? This shaft will not translate in the x direction. So we are again putting one more constraint on it. So total number of constraints are now 5, and the rod can just translate. Sorry, it can just rotate about x-axis. So total degrees of freedom in this case is 6 minus 5. That is only 1. Okay, so that is how we can calculate the degrees of freedom. Okay, so this is how we can calculate the degrees of freedom for a pair. So this is for a pair, I will say. But we are talking about mechanism, not just pair. So if we bring them together, if we bring all these terms together, we have to understand now how we'll make the mechanism out of it. So I'll say a linkage first. What is linkage? Linkage is, or let's say rather than linkage, let's start with a kinematic chain. Kinematic chain. So we'll first make a kinematic chain. Kinematic chain is nothing but the assembly of the links. So we are assembling these links together. We know what is link. We know how to make the joint, right? And we have possible relative motion between them. Then we'll make a linkage out of it. What is linkage? Whenever we are fixing one link to ground, okay, then we call it as a linkage. So take a kinematic chain, fix one link to the ground, okay. One of the link of kinematic chain is fixed to the ground. Okay, then we call it as a linkage. And what is the result out of it? And linkage will make a mechanism. Okay, and when we say it is a mechanism, if motion of any one of the movable link results in definite motion of others, then that linkage is called as mechanism. Motion of one causes constrained and predictable motion of others. Okay. Others, then we call other links, then we call it as mechanism. And we know if you combine mechanisms, we'll get a machine. I hope now things are clear. How we'll first make a kinematic change means assembling the links together by joints. Joint means pairs. Making a linkage. Linkage means fixing the one of the link of the kinematic chain to ground will make a linkage. And if we give one motion to the one, and if we are getting constrained and predictable motion of the other links, then we call it as a mechanism. And if we combine the different mechanisms, we can make a machine out of it. Okay. So now we understood how machines and how the mechanisms are made. Now it's time to understand how we can calculate the degrees of freedom of mechanism, because we are interested in mechanism, not just at the pair level. So let's write down heading movability of mechanism or degrees of freedom of mechanism. Movability of mechanism. Okay. So how we calculate the degrees of freedom of mechanism is, we know we have 6 degrees of freedom for an link, but out of, in a mechanism, we know one link is ground, one link is fixed to the ground. So we suppose if total n number of links are there, okay, n is total number of links, then n minus 1 will be the total number of movable links. Okay, so total degrees of freedom is 6 into n minus 1. If we don't put any constraint on the links, but that is not possible. Whenever we are making a pair, we are putting the constraints, right? So either we'll have, let's say, pairs with 1 degree of freedom. So 1 degree of freedom means P1, I'll say, is number of pairs with 1 degree of freedom. It means we are putting 5 constraint on it. That's why 5 times P1 I'm writing here, minus 4 times P2. P2 is number of pairs with 2 degree of freedom. Okay. Similarly, we have 3 times P3 minus 4 times, 2 times P4 minus P5. Okay. So P3, P4, and P5 are the same, with the 3 degrees of freedom, with the 4 degrees of freedom, with the 5 degrees of freedom. Okay. So this is how we will calculate the total degrees of freedom of a mechanism, right? We have n minus 1 number of movable links. So 6 times n minus 1 is the number of degrees of freedom for the movable links, but we are making the pairs which will either have 1 degree of freedom, 2 degree of freedom, 3 degree of freedom, 4 or 5. And if 1 degree of freedom is there, then we are putting the 5 constraint. If 2 degrees of freedom means we have 4 constraints. That's why we are multiplying with the 4 times P1, 5 times P1, 4 times P2, and so on. Okay. So this is how we will calculate the total degrees of freedom. Now we are studying the planar mechanisms in our subject. Okay, in our syllabus, we are focused only on the planar mechanisms or plane mechanisms. Plane mechanisms means mechanisms which we can draw on a paper, okay, or in the 2 dimension. So in 2 dimension, only 3 degrees of freedoms are possible. One is translation in x direction, translation in y direction, and rotation about z direction. So these are the 3 possible degrees of freedom. So total degree, this formula will further simplified as 3 times n minus 1 minus 5 times p1, sorry, 2 times p1 minus 1 time p2, because we only have 3 degrees of freedom, and if we are putting if we have making a pair with a 1 degree of freedom, means we are constraining 2 degrees of freedom. That's why 2 times p1 I should write, and 1 times p2, means if we are making a pair which will have 2 degrees of freedom, then um, it means we are putting one constraint on one direction, okay, or one motion. So that's why 3 times n minus 1 minus 2 times p1 minus p2 is the simplified formula for a planar mechanism, and this is called as Grubler's criterion. Okay, this is the Grubler's criterion. There is one more criteria, that is Kurzbach's criteria. What is that? Let's try to understand. Kurzbach's criteria. Suppose if we have a linkage with a single degree of freedom only, okay, if we have a linkage with a single degree of freedom only, it means p2 will be 0, right? In that case, this f will become 3 times n minus 1 minus 2 times p1. This is called as a Kurzbach criteria, where p2 is equal to 0. The meaning of p2 is equal to 0 means this is a linkage with a single degree of freedom only. Okay, means we don't have a pair with a 2 degree of freedom. All the pairs are with a single degree of freedom. I hope it's clear. So this is, you can say, a simplified version of the plane mechanism. So let's try to understand this through some example. Suppose I want to make a mechanism with a 1 degree of freedom. Okay, so I will say 1 is equal to 3 times n minus 1 minus 2 times p1. This is the formula for the Kurzbach's criteria formula we know. And I want to calculate how many links and basically how many pairs I have to make and how many links I need in order to make the mechanism with a single degree of freedom. Okay, yeah, just give me a minute.
You are currently the only person in this conference.
Yeah, so suppose I want to make a mechanism in which only 1 degree of freedom is there, then how I can write is 1 is equal to, because this is the degree of freedom, f is equal to, the formula was like this, right? And we want to make a mechanism with a single degree of freedom, then I should write it as 1 equal to 3 times n minus 1 minus 2 times p1 So the simplified formula will be 2 times P1 equal to 3n minus 4, right? So if I take n equal to 4, for example, then what will be the value of P1? P1 will also be 4, right? Because 3 into 4 is 12 minus 4 is 8 divided by 2 is 4. So if you put into this formula, we will get the value of, for different value of n, we'll get the different value of P1. So if n is equal to 5, do we have any value of P1? No, we'll get some, because 15 minus 4 is 11. 11 by 2 is not a not integer. So we cannot make basically a mechanism with a single degree of freedom with an odd number of links. Okay, so that is the first learning we got. Okay, P because so as to have a possible linkage, we have to have the even number of links only. This is the first learning. So n is equal to 6. If I use what will be the value of P1? 18 minus 4 is 14. 14 by 2 is 7. So P1 is equal to 7. If I take n is equal to, let's say, 8, P1 will be equal to 9. Sorry, P1 will be equal to 10, because 24 minus. We can understand from this is, if we have 4 links, we have 4 pairs. So we don't have an excess, no excess turning pair. If you have 6 link, we got 1 excess pair, 1 excess turning pair. And if we have 8 links, then we have 2 excess turning pair. So as we increase the number of links, what is happening? Number of excess pairs are also goes on increasing. Pairs are also increasing. Okay, so this is the learning what we got from this relationship. I hope it's clear. So the basic formula, I'll repeat. Degrees of freedom can be calculated by using, general formula is 3 times n minus 1 minus 2 times P1 minus P2. Okay. That is n minus, in bracket, 2l plus 1, and the number of pairs are also can be calculated by n plus l minus 1. Okay, so these are the formulas which we should know. Here n is, I have already explained, n is total number of links, but new concept here is l. What is l? L is number of loops. Okay, so either you can use this formula in order to calculate the degrees of freedom, or you can use this formula as well. Okay, so let me just give one simple example where we can calculate this degrees of freedom using the second formula. And figure here. Okay, so we got link number 1, which is ground, link number 2, link number 3, link number 4 is this, link number 5, 6, 7, and 8. Okay, so if you see this figure, the total number of links are 8. Number of loops here are, how many loops are made by the connection of links? In this case, it's here and one is here. So total number of loops are 3. Okay, so the degrees of freedom now can be calculated by using formula n minus 2l plus 1. It will be 8 minus 2 times 3 plus 1, so 1. Okay, and how many pairs are there? P1 means number of pairs with 1 degree of freedom. Using the formula n plus l minus 1, that is 8 plus 3 minus 1. We should get the same. Okay, so let's try to count them. I'll use the green color. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 connections, and we have or 10 pairs, and from the formula as well we can calculate it. Okay, I hope it's clear. So now we got the concept of the rigid body pairs, and now we should try to make a mechanism out of it. So what kind of mechanism we can make? So either we can make a 4-bar chain mechanism, or a single slider crank mechanism, or the double slider crank mechanism. So let's try to study these mechanisms or let's try to study these planar mechanisms in detail one by one. So I'll start with the 4-bar chain, the simplest mechanism. Okay, it's a most fundamental plain kinematic chain, we can say, consists of 4 rigid links connected in the form of quadrilateral by 4 pinpoints. Okay, so the link which is rotating here in the 4-bar chain is called as a crank. The crank is one which completes the whole revolution. Okay. The other is, let's say, other kind of link is rocker. The rocker means the one which oscillates, and the link which connects this crank and oscillator is called as a coupler. Okay, and one link will be fixed. So this is how 4 different links are distributed in the these are the possible links in case of 4-bar chain. Okay, so either we can have a crank, we may not have, depending on the cases, but these are the possibilities in a 4-bar chain. We can have crank, we can have a rocker. If we have a crank and rocker, the connection is a coupler, and one has to be fixed link, because in mechanism we know one link is fixed. The basic we should know in order to make a mechanism. Yeah, what we understand from this figure is, I'll use a laser pointer. The link A, B, C, and D. If the length of one of the link is more than sum of the other 3 links, then basically you cannot make a joint, right? We cannot make this joint here. So it is not possible to make a mechanism if length of one link is greater than the length of other 3. Okay, so this is the basic learning which we have got now. Okay, so in order to make a mechanism, we should have, let's say, we should not satisfy this criteria. Okay, or a plus b plus c should be greater than d. Okay, in general, in this case, then only it is possible to make a, or sum of the 3 links should be greater than the 4th link, then only we can make a 4-bar chain. And depending on now the length of other links. Okay, suppose for example, I'll take an example here. Let's take example here, this example. I'll say shortest link is D here. Shortest link is, for example, D. Okay, for example, in this case. So there is one more classification we should know, or one more criteria we should know is length of the shortest link. For example, here D is the shortest link, and let's say C is the longest link. Okay, longest is C. Okay, so D plus C, if it is less than the sum of other two, A plus B. Okay, let's try to understand what I'm saying. The sum of the shortest link and the largest link is less than the length of the other two links, then that kind of mechanism is where we can imagine a crank. Okay, or there we can imagine at least one rotating link. Okay, see, because if this C link comes to the right hand side, okay, if D plus C is, let's say, greater than A plus B, we cannot have this situation, right? This is possible only when, or we can bring this C to the horizontal like this, which is shown in the below figure, only when A plus B is more greater than D plus C, right? So that's why, um, and here it is possible that A can make a complete revolution out of here. Okay, so if this condition is satisfied, then we can say it as a class 1 mechanism. Okay, and if D plus C is greater than A plus B, we call it as a class 2 mechanism. Okay, and here we have a Grashof law. What it says for class 1, what it says is, in a 4-bar mechanism, we will have at least one revolving link if sum of the shortest and the longest link is less than the sum of the other two links. Okay, so if this is, so basically in short, Grashof law says that in class 1 type of linkage or 4-bar chain, we have a crank, or at least one rotating link, in other words. Okay, and whenever we have this kind of situation, length of shortest plus largest is greater than other two, in that case we cannot have a rotating link, and so this is the situation. You will get a rocker mechanism. Okay, so basically these two links will just oscillate. They will not, none of them will have a mechanism. Okay, in order to have a class 1 mechanism, or in order to have at least one revolving link, the length of largest and shortest link should be less than the length of other two. Okay, so whenever a question comes, what is a possible mechanism for a given figure, first of all you have to check whether it's a class 1 or class 2. If it is a class 2, it is clear that it will have a rocker mechanism, because length of the shortest and largest link is greater than other two. We cannot have a complete revolving link here. That's why it's a clear rocker mechanism. But whenever it's a class 1, okay, whenever it's a class 1 mechanism, that is D plus C is less than A plus B, there we have different possibilities. Depending on which link you are fixing, so either you can fix the shortest link, okay, or link opposite to the shortest link, opposite to shortest or adjacent to the shortest. Okay, so if link adjacent to the shortest link is fixed, then what will happen? Look at this figure, try to imagine. So in this current figure, link D is shortest link. So this, rather than fixing D, I am fixing A link, for example. A is adjacent to the D. So here it is clear that D will have a complete revolution and C will act as a or you can say rocker here. Okay, so this is the situation. I am explaining through a laser pointer now. If I'm fixing link A rather than fixing link D, what will happen is D will rotate completely and B will oscillate and C will act as a coupler. So this is an example of crank rocker mechanism. Okay, so whenever we fix a link which is adjacent to the shortest link, we'll have a crank rocker mechanism. Okay, whenever a link opposite to the shortest link is fixed, okay, suppose if I am fixing this, okay, rather than fixing D, I'm fixing B. So what will happen? None of them will have a complete rotation. So B, A and C, both of them will just oscillate, right? So we can say it's a rocker mechanism or double rocker mechanism, we can say. Okay, you can either call it as a rocker mechanism or a double rocker mechanism. Double rocker. And what will happen if we pick the shortest link? If you fix the shortest link, then we will have a double crank mechanism. Double crank mechanism. Let's take an example here. So here D is fixed. So B can also rotate and C can also rotate. Okay. So this is the situation here. Both both A and C can have a complete revolution, and B is, let's say, a coupler between them, and link D, which is shortest, is fixed. Okay. So this is how you should proceed. Whenever D plus C is greater than A plus B, it is clearly a double rocker mechanism. You don't have to check which is fixed link and all, but whenever it's D plus C is less than other two, in other words, length of shortest and largest link is less than other two, then depending on which link is fixed, we can have a different type of mechanism. So if shortest link is fixed, as mentioned here, we will have a double crank mechanism. If the link opposite to the shortest link is fixed, then we have the double rocker mechanism, and if crank rocker mechanism. Okay, so that's all about the class 1 and class 2, but we can imagine a situation where D plus C can be equal to A plus B. It can be a special case, right? And in this special case, so what are the possibilities here? Let's say here I explained here D plus C is equal to A plus B. Length of shortest and longest is equal to the length of other two. Then it's a special case, or you can call it as a class 3 type of mechanism. Here, depending on which link you are fixing, we will have different kind of mechanism. Okay, so let's take an example here. It's a parallel crank 4-bar linkage. In the figure number A, okay, Imagine a mechanism in a coupled wheel of a locomotive where two wheels are coupled together like this, and the link A and C will have a complete rotation, right? So it's a double crank mechanism we will get here. Crank mechanism. CC I will write here. Okay, crank mechanism. So this is an example of a coupled wheel of a locomotive in which rotatory motion of one wheel is transmitted to the other wheel, and the link D is treated as fixed link here. Okay, so you can imagine this is a double crank mechanism. Then in the next figure, so this is a different situation. This is parallel case, okay, where the opposite links are of same size, and this is a deltoid case. In deltoid case, we have adjacent links of our same size. So here link A and D is of same size, right? And link B and C are of same size. So this is the deltoid case. In deltoid case, depending on which link we are fixing, we have different kind of mechanism. If the shortest link is fixed, in case of deltoid, if the shortest means either A or D is fixed, we will have crank mechanism. And if you fix largest link, largest means either B or C, in that situation we'll have a crank rocker mechanism. Okay, so these are all possible mechanisms in the 4-bar chain. I'll repeat from the beginning. We have seen the case of class 1. The length of shortest and largest is less than the other two, and here depending on which link we are fixing, we have different types of mechanisms. Then the class 2 mechanism, where length of shortest link and the largest link is greater than other two, here we will always get a rocker mechanism. Okay, and the third case, where you can call it as a class 3, or the special case where length of smallest and largest link is equal to sum of the other two. Okay, here either we can have a parallelogram case where the opposite sides are of same size or same length, or the adjacent sides are of the same length. So either parallelogram or a deltoid. In parallelogram, we'll have a crank mechanism, and in case of deltoid, depending on which link we are fixing, we will either have crank or crank rocker mechanism. Okay. Four-bar chain. Now let's try to understand some terminologies of 4-bar chain before we jump into the slider crank mechanisms. The first concept is mechanical advantage. What is mechanical advantage? Mechanical advantage of a mechanism is ratio of output force to the input force, or output torque to the input torque. Output torque to the input torque. Okay, we know whatever power we are giving as input will get a similar output power. So what is power? Power is equal to torque into omega. So T2 into omega 2. So for example, in this mechanism, T2 is the input link and T4 is the output link. So if you do the motion like this, 4 will turn like this, and T2 omega 2 is input power, and T4 omega 4 is the output power. Okay, and mechanical advantage will be now T4 by T2, or you can write it as omega 2 by omega 4. Why? Because from this relation we know that torque is inversely proportional to the omega. Okay, hence we can say omega means velocity, angular velocity here, and torque ratio is inversely proportional to the velocity ratio. So mechanical advantage you can express as output torque to the input torque, or input velocity to the output velocity. Okay, so that is the first learning we have for the 4-bar chain. Another learning for it is transmission angle. What is transmission link here? This is our input link. This is our coupler. So angle between output link and coupler is transmission angle mu. Okay, so in exam, what will happen is they may ask us to find the what is the maximum possible transmission angle and what is the minimum possible transmission angle for the given figure. Okay, so let it to okay. Okay, what will happen? Mm, is so this is our link A here overlapped, and now we'll have a link B which is a little bit longer. So it will turn to this side, and this is our link C. Okay, our C now. So if I rotate, let me use the laser pointer here. If I rotate link A clockwise until it falls on the horizontal surface, then we'll get the smallest transmission angle, right? So this is the smallest possible transmission angle, mu minimum. So I will say whenever this theta angle is 0, theta is equal to 0, what we'll get is we'll get a minimum transmission angle for this figure. Okay, and if I I'll use green pen now. If I move this to the left hand side, okay, okay, so what will happen here is this is our link A now, and B is a little bit longer over here, and C. This is B and C. So this is our mu max in this situation. So I'll say when theta is 180 degree, then we'll get a maximum transmission angle. Okay, so this is the way we can calculate the minimum and maximum transmission angle in case of the mechanism. So we have to look into the type of the mechanism here and figure it out at what value of theta. So there's the theta angle. Theta is in between the angle between the ground link and the input link. Angle. Okay, and by using mathematical equations we can find it. So this is a theoretical background behind it. So that's all we have for the 4-bar chain mechanism. Now it's time to study the single slider crank mechanism. The slider crank chain. Okay, the slider crank chain. When one of the turning pair of a 4-bar chain is replaced by a sliding pair, we call it as a slider crank chain, single slider crank chain. Okay. So let's see the figure here. In this figure, let's say figure number A, we have link number 1, link 2 is crank, link 3 is a connecting rod, and link 4 is a slider. Okay. We have a crank, connecting rod, we have a slider, and we have ground. Okay, and the figure number B is more little bit sophisticated version of it, where that link 4 is a piston and link 1 is part of the cylinder here, you can say. Okay, so this is the first inversion. So in 4-bar chain, the different inversions were like crank rocker mechanism. So here, depending on which link we are fixing, we have different inversions. So the first inversion is I'm showing here. First inversions means link number 1 is fixed. Whenever we are fixing first link, this is what we'll get. And this is an example of a reciprocating engine or reciprocating compressor. Engine or reciprocating compressor. So where link 1 is fixed, and if we move link number 4, link 3 will move and link 2. So for each inversion, we should know what are the applications of it. So application of first inversion is reciprocating engine or a reciprocating compressor. The reciprocating compressor will be just opposite of it. Though the link number 1 is fixed, the input link in case of compressor will be 2 and output link will be 4. Whereas in case of reciprocating engine, 4 will be input link and link number 2 will be the output link. That is the only difference. Coming towards the next slide, we have second inversion. In second inversion, link number 2 is fixed. Okay. So before we were fixing the link number 1, and now we have to fix the link number 2. Okay. So this was our first inversion. Now this is our second inversion. Link number 2 we are fixing. So once the link number 2 is fixed, what kind of mechanism we can create out of it? The application of second inversion are Whitworth quick return mechanism, and another application of it is rotary engine. Okay. So what is Whitworth quick return mechanism? So it is a mechanism we generally use in the workshops to cut the metal. If you remember the shaping and planing machine, the idea there is during cutting stroke, the tool should move slowly, whereas our tool should cut the material and the return stroke will be the idle stroke. So in that case, tool should not waste time and it should return quickly. That's why the name itself indicates here it's a quick return mechanism. So cutting stroke is a little bit longer than the return stroke. Okay, so return stroke is quick because we are not cutting the material during that stroke, but in the forward stroke or the cutting stroke. So you can imagine a situation here. So this figure B is converted to the figure C. In order to make this mechanism, I'll just dark with a red color. I'll just mark with the red color the mechanism. So you can imagine. So you can compare figure B with C. Same figure. So we are just connecting one more link number 5, to the tool. And what is happening here is during the cutting stroke, the tool will have this much complete revolution. Okay, angle C double dash A B double dash. Okay, obtuse angle C double dash A B double dash. Okay, and during return stroke we have acute angle level. Okay, so same angle but the acute angle. So you can clearly see here we are having obtuse angle during cutting stroke and acute angle during return stroke. Okay, so that's why we are, that is the basic idea why we are getting the quick return. Okay, why our return stroke is faster than the cutting stroke. Okay, so let's call this obtuse angle as theta and this acute angle as beta. Theta and beta. So I'll say quick return ratio can be written as or time for cutting divided by time of return can be written as theta by beta. Okay, so cutting time is theta, return time is beta in this case. Okay, I hope it's clear from this figure what is the logic behind the quick return mechanism. Okay, because we are rotating by an obtuse angle during cutting and we are rotating by an acute angle during return. That is why time for cutting is more than time for return, and that can be achieved by using this second inversion of the side. The another advantage or another application of second inversion is rotary engine. So here you can clearly see in case of rotary engine, this is a figure. I'll highlight the mechanism here. Link number 2 is fixed. This is link number 3, link number 2. Okay, so what we are doing is to the link number 3 we are attaching link number 4, and link number 1 is part of, let's say, the whole cylinder or cover, cylindrical cover. Okay, which is outline of this rotating engine. So link number 2 we are fixing again here, right? Link number 2 is fixed, and for link number 3 we are attaching the link number 4, and link number 1 is taking this outer shift and acting as a cylinder. So this is how we can use the second inversion of the single sided crank chain in rotary engines. The third type of inversion is where we are fixing the link number 3. Whenever you are fixing the link number 3, the application of this, you can make it in the case of oscillating cylinder engine, or you can make in the crank and slotted lever mechanism. Okay, this is similar to the Whitworth quick return mechanism. The only difference here is like here, because you can clearly see here also we have theta and beta, and we can expect the during let's say cutting stroke, we will have the larger time, and during return stroke we have the lesser time. Okay, and but it is slightly different from the quick return mechanism, because here we are fixing the second link, not here we are fixing the third link, not the second link. In crank 3 of the with work quick return mechanism is longer than the fixed link. 2 of the slotted lever mechanism is shorter than the fixed link 3. Okay, so here you can clearly see link 2 is shorter than link 3. Okay, so crank is shorter, third link is bigger, and that is what we are fixing here. Okay, and that is the difference. And in the link 4 we are making slot. Okay, that's why the slotted lever they are saying. Link 4 is a lever in which we made a slot which is sliding, and we are getting the required motion for our cutting tool. Okay, so this is a little bit different than what we have studied before as Whitworth quick return mechanism. Okay, I hope it is clarified. So this is the third inversion, and the last inversion is fourth inversion. And the application of fourth inversion is hand pump. So in the fourth inversion, fourth link is fixed. So we are fixing the piston. Is now I'm taking link number 1 and I'm making link number 1 like this. Okay, this is my link number 1. Link number 2 is this one. This is link number 2, and I'm making the link number 3 something like this. Okay, and link number 4 is fixed. So this should be connected to the link number 4, and that link has to be fixed, right? This link number 4 has to be fixed. Okay, this is link number 4, this is link number 3. So if you just extend this, in reality it will look like this, and if you extend this bar further down, you will get figure number B, that it's looking as hand pump. So they are just modifying this figure like little bit like this, you know, for the hand pump. Okay, so if you fix the link number 4 and to the link number 1, if you make a plunger out of it. Okay, so we are fixing the plunger to the link number 1, and the link number 4 is fixed, and if you are giving a cylindrical shape to it, then it will act as a hand pump. Okay, so fourth inversion, the application of fourth inversion is the hand pump here. Okay, so that's all about the single slider crank chain mechanism. Another kind of possible mechanism is double slider crank chain. Okay, in double slider crank chain, we have 2 sliders here. If you take a 4-bar chain and you remove 2 turning pairs, or you replace 2 turning pairs with the sliding pairs, then we call it as a double slider crank chain mechanism, and it will look something like this. So this is the first inversion. Here only we have 3 inversions, because link number 2 and link number 4 are the sliders. So we can either fix one of the slider, right? So it will become the same thing. So that's why we only have 3 mechanisms, 3 inversions. In first inversion, we are fixing the link number 1, and the application of it is elliptical trammel. Okay, here look at this figure. Link number 1 is fixed. Link number 2 is piston. Okay, link number 1 is fixed, link number 2 is piston or slider, link number 3 is okay. And yeah, so basically the slider 2 and 4 is sliding in between the slots of link number 1. So the bigger picture will look like as figure number B here. And if you just elongate this link number 3 to point C and just rotate this point C, you can trace a ellipse out of it. So depending on how long you make this point C, you can trace different sizes of the ellipse. Okay, so this is C1, C2, C3, and so on. So if you go away from the point number B, you will get bigger and bigger ellipse. So elliptical triangle will help us to create or draw the ellipse. Okay, yeah. So what is the equation of ellipse in this case? X square divided by BC is equal to 1. Okay, here the B point will come here and then C will be here. So B to C will be, you can say sorry, yeah, if B comes here then A will come here, so this will be AB, right? And if B comes here and C comes here, then this outer length will be like oh no, sorry, this is BC. So BC is, you can say, along the x-axis, which is minor axis, and along the y-axis, if you have major axis, then AC will be the length of it. Yes. So let me just draw here. This is A point here. This will be C, and B will be somewhere in between. Okay, and this is a situation where we have A at the extreme point, B in between, and C here. So BC will be here. In this case, the minor axis. Okay. So I think it's enough if I just draw like this. Let me remove the other stuff so it will be more clear. Yeah. Okay. So AC is the major axis and BC is the minor axis. So x square by BC square plus y square by AC square will be 1. Will be the equation of ellipse which we can generate out of it. Okay. If AC and BC are the same, then x square plus y square is equal to AC square will get, if AC is equal to BC. Then we can create a circle out of it. So elliptical triangle will not just will help us to create the ellipse, but also a circle, depending on the cases. What is the value of A to C and what is the value of B to C? Okay, yeah. So this is the first inversion, elliptical triangle. Second inversion, we can fix the link number 4, and the exam application of it is Scotch yoke. Scotch yoke mechanism is used to generate the function. It is sine and cosine function generator. So for example, look at this figure. So as you are rotating this slider, so here link 2 is again slider and link 4 is again slider. Okay, this link 4 is also sliding here, left and right, and link B is also sliding in this slot. Sorry, the link number 2 is also sliding in this slot. So if you rotate that, or if you turn this link number 3, what will happen if you turn it counterclockwise? The link number 4 will come towards left hand side, right? Let me draw it here. If you bring it like this, um, depending on at what angle you are rotating it, you will have some distance traveled by the link number 1 with respect to this vertical line. Okay, and similarly, if you rotate it to the to the clockwise direction, this link number 1 will move towards right hand side. So basically, if you can imagine a sine curve here or the cosine curve, depending on what angle you are rotating, the magnitude you can trace here. Okay, so basically, let's assume the situation where this block is here. Okay, and okay, somewhere some kind of this kind of situation. The situation is here, angle is 0. So here this is theta is 0. So at theta 0, let's say the displacement is displacement is 0. But as you go on increasing the theta, the let's say if you are rotating clockwise direction, what will happen is the rod will move towards right hand side, and you will have a positive displacement out of it until some time. And if you continue rotating the rod towards continue rotating this link number 3 towards downward side now after this point. So this is the situation. B will be somewhere here. So initially it is here, then here, then here. So this is the situation where B is horizontal. Okay, B is on the horizontal line. Here B is on vertical line. And if we bring again B to the horizontal line here somewhere, okay, B again on vertical, then this point will come here. Okay, and now if you again rotate it, what will happen? If you again rotate it, then the slider will move in the left hand side direction and will have a negative similar curve out of it. Okay, so we can create basically a sine and cosine function out of it. So in general, Scotch yoke is a function generator, we can say, and this is the second inversion of 4-bar chain where we are fixing the link number 4. Before that we have fixed the link number 1. Here we are fixing the link number 4. So basically link number 4 is one of the slider we are fixing. Okay, but to the link number 1 we made like a slider, and in that we made a slot to make this kind of second inversion out of it. Okay, and the last inversion is the third inversion for the double slider crank chain, and the application of it is Oldham's coupling. It's fixed. And application is Oldham's coupling. Coupling we know is used whenever there is some kind of misalignment in between or basically to join two shafts we need coupling. We know whenever two shafts are with angular misalignment, we use knuckle joint or universal joint there, right? To make a coupling. But whenever an axial misalignment is there, okay, whenever an axial misalignment is there, in that case we have to use the Oldham's coupling. Look at this figure here. This is the shaft, this is the first shaft. An axis of shaft is like this, and this second shaft, the axis of shaft is like this. So you can clearly see there is a misalignment, there is axial misalignment in between. Transmit the motion from the shaft number 1 to the shaft number 2. We need a coupling, and that coupling we have to use is the Oldham's coupling. Okay, here the link number 3 is fixed. Okay, So these are the frames, we can say, which will act as a link number 3. Link number 2, 1, and 4 are like the projections which we are making on the flanges. So link number 2 is flange of shaft 1, link number 4 is a flange of shaft 2, and we have made some slots in which the link number 1 fits. Okay, look at this, how it is fixing. By this project, these projections will fit into this, and these projections will fit into this slots, and we'll get the possible coupling out of it. Okay, so the third inversion is Oldham's coupling, and we use it in order to have the motion between the two shafts, which are. That's all we have for the double slider crank chain, and that is the last point of this topic. Okay, so just to recall what we have studied in this chapter is we understood the concept of first the rigid body and resistant body, and how we can combine them, or how we can connect them or join them together. So different types of joints we have studied: binary, tertiary, and or pairs, we can say closed pair, unclosed, higher pair and lower pair, and so on. And what kind of motion which we can have, either completely constrained motion or successfully constrained motion or incompletely constrained motion out of it. And then we studied how to make um, uh, uh, how to make a linkage out of it, or the kinematic chain out of it, and then how to find the degrees of freedom for any mechanism. And then we studied the 4-bar chain, single slider crank chain, and double slider crank chains in detail. Okay. I hope you understood all this topic, and thank you all for joining this session. Yeah, thank you.